Let's solve now physics exam 2016. Okay, so question 5. I started with the last question, but I don't think it's a problem. We are going to solve the whole the whole exam. So let's read the question, and then I'm going to put the question 5.1, 5.2, and there goes forward. Okay, so as shown in the figure, a rectangular glass blocks with an index of refraction of n2. So the index of refraction of n2, so there is a glass over here. Okay, let me just here, there is glass over here. Okay, with the index of refraction n2. Okay, so are attached to the upper and the lower planes of the rectangle glass block. So this is another glass. So this is another glass with the index of refraction n1. Okay, just so that we don't have very, so one here. At the light ray enters the glass block at the point A from the vacuum. So in the vacuum, you need to remember that the index of refraction in the vacuum is 1. Okay, so in the incident angle, this angle over here, theta, the light ray reaches the point B after repeating a total internal reflection in the block. The speed of the light in the vacuum is denoted as c. Okay, answer the following question. So just I think for this question over here, all you need to remember two things. Number one, look, if you had a light going like this, okay, so 1 second, and like this maybe, okay, so you need to remember that there is a relation between this and this over here, these angles. Okay, Snell's law. Okay, so let's say that here n1 and here it is n2. Okay, so n1 multiplied by sine of alpha is equal to n2 multiplied by sine of theta. Okay, now look, here we have it going from where to where? We have it going from, let's say this is the direction of the light. Okay, so is it going from the bigger index or the smaller index of refraction? Well, you just need to look at the formula over here if you forget. Okay, look, this is an equality, right? So which sign is bigger? If this angle over here is smaller, then this sign over here is smaller, right? And this sign over here is bigger. Then n1 must be smaller from n2. Why? Because there is an equality. If n1 multiplied by sine of alpha is equal to n2 multiplied by sine of theta, but this sign is smaller than this one, so this must be bigger than this, right? Now, the second thing you need to remember to solve this question, and this will be the last thing, and then you can solve it by yourself, is the way to total reflection. Okay, total refraction, reflection, total reflection, I think the name in English. Okay, so look, let's say now the light going like this, here, this is the light going, and then it goes like this maybe. Okay, so it is going n1 and 2. Okay, so this is of delta and this is alpha. Now look, if it is going from the medium of the bigger index of refraction to the smallest, you can have a total reflection. How? Look again, n2, now sine of theta is equal to n1 sine of alpha. You can see clearly that the alpha is bigger, right? So the sine of alpha is bigger than the sine of theta. So N2 is bigger than N1, and you can, if you do it in the right angle, you can do it as such as when this reflection beam comes out, it goes and goes, and it seems like you have a total reflection, okay? So you will only have the reflection part over here, you won't have it going out there. It's like if this was 90 degrees, so you will have the n2 sine of theta equals to n1. This is like 90 degrees, so it is like 1. So you have that sine of theta is equal to n1 divided by n2, okay? So this is what you need to remember. Now if you want to try to solve it by yourself, go ahead. Now let's go to solving 1.1, okay? So he's asking you the expression for this sine of theta, okay? So this is what he's talking about, okay? So remember the first thing that we said, look over here, okay? So we'll have that the n of this part over here, which is 1, because he's told you that it's coming from the vacuum. So 1 multiplied by sine of theta must be equal to the n1 multiplied by sine of this omega, I think. So sine of omega must be equal to sine of theta divided by n1, and this is actually the answer over here, okay? Sine of theta divided by n1, simply applying Snell's law, okay? So straightforward. Snell's law, okay? Let's go to 1.2. So now let's solve 5.2. Now he wants the relation, the condition between n1 and n2 that should satisfy in order for the block to make a total refraction, a total internal refraction. It was refraction, yeah, this is how we call it, take place in the upper and lower planes, okay? So total refraction, okay? So this is what happened. You have one second. Spoilers. So remember, I already showed you that in Snell's law, the total reflection, so n1, let's say sine of some angle over here, it doesn't matter, it can be any angle, alpha equals to n2 sine of another angle, so it doesn't matter. I can't use this one, a, okay? So if you want a total reflection, n1 must be bigger than n2, okay? Now remember, sometimes if you want a form for you to remember it, so this is you over here, and let's say there are some things over here in the water, okay? This is water, okay? This is water, so the light comes in and then total refraction, and you can't see it, okay, sometimes. And water, n1 and n2, n1 is bigger than n2, okay? So what am I trying to tell you? That we have a relation when we divide them. If we have n1 divided by n2 over here, n1 and n2, n1 is bigger than n2, so this division is always bigger than 1, okay? Like if n1 was 4 and n2 was 2, this would be 2. If it was 3 divided by 2, this would be bigger than 2, okay? Because this is always bigger than this one, so we will always have it bigger than 1, okay? So this is our answer. One second, over here. So C again, okay? So now let's go to 5.3. Now 5.3, so he's asking you the condition that this angle must satisfy in order that the total internal reflections take place in the upper and lower panels of the glass block. So what is he trying to tell us? Well, he's telling us, one second, let me just, yes, now look, the condition that this must satisfy for this total refraction to occur, okay, for the total reflection to occur, for the total internal reflection. Okay, so look, the first thing you need to note in this drawing over here is that this line over here is parallel to this line over here, okay? So, and this is a line that is cutting them. So, this line over here is theta 2, okay? This was very big, so over here. Let me try to do it small. One second. Here, and then like here. Perfect. And the second thing we need to talk about is, let's trace this line over here, okay? A perpendicular line over here, okay? So by the law for the, like, there is a law of the reflection, right? The second law, that this angle over here, this angle, okay, one second, this angle over here is the same as this one, right? When the beam of light hits, it goes out in the same angle. So this one over here is the same. I will need to write it. So this, now I'm going to call this line of this angle over here alpha, okay? Alpha is this part over here. Let me do it in red. This is alpha, okay? So what is the condition? Okay, so look, but in Snell's law we have that n1 multiplied by sine of alpha, okay, must be equal to n2 multiplied by the sine of the angle that the beam of light goes out, right? Something, maybe omega, I don't know. But you can see that the light is not going out. Why? Because you consider it like if this angle over here was 90 degrees, okay? So as long as, this is how you think about, as long as this is bigger, okay, as long as n1 sine of alpha is bigger than n2, why just n2? Because the angle going out is 1, okay, this is valid, okay? So sine of alpha must be bigger to n2 divided by n1. But he did not give us alpha. He wants it in term of what? He wants it in term of this angle over here, right? This one. So what is the relation between alpha and this angle? Where they are complementars, right? What do I mean by this? Alpha plus phi is equal to 90 degrees, okay? When this happens, you have that sine of alpha is equal to cosine of alpha from trigonometry of cosine of phi, okay? So cosine of phi, this, which is equal to, this is bigger or equal to n2 divided by n1, okay? This is from trigonometry, okay? So we have that cosine of phi bigger than n2 divided by n1. Cosine of it here, n2 divided by n1. For 5.4, another thing that I forgot to say in the beginning of the video, you need to remember that n is equal to c divided by v, which being v is the velocity in this medium over here, okay? So c divided by v, okay? So by this you can solve it, okay? So find the time at which the light entering at point A reaches point B, penetrating through the glass block. The distance between the two planes, including point A and B, is denoted as L, okay? So we know this distance over here is denoted as L. And now what do we need to find? Well, the time. So what is the time? Now, if you remember, v is equal to distance divided by the time. So time is equal to what? Distance divided by v, right? So what is our objective? One, what is the distance? Distance is equal to what? Because the distance is not L, okay? He's going this, this, this. So our distance is A A, B, and D, okay? Let's actually call this points over here. So we have point A already, so let's call this point B. We have point B already, so let's call this point C and this point D, okay? So the distance is A to C, C to D, and D to B. What is the velocity? Well, N1 is equal to C, not this C over here, C the velocity of the light, okay? He tells us over here the velocity of the light in the vacuum, okay? So C divided by V. So V is equal to C divided by N1, okay? So now, one second. So V is equal to C divided by N1. And look, our term T is equal to D divided by V. So if T is equal to the distance that we didn't find yet divided by V, so it's divided by C multiplied by N1, okay? So this is the term that we need to look. So T is equal to D multiplied by N1 divided by C. Now if we find D, we are finished, right? So let's find D, okay? So how can we find D? Well, by a bit of trigonometry, okay? So look, here we go. So remember, this was also phi, okay? So what is this part over here? Well, the line from A to C is equal to what? Is equal to the hypotenuse of this triangle over here, right? This triangle over here, right? So what can we say about it? Well, we know that cosine of phi is equal to what? To this side over here, which I'm going to call it A, divided by AC, okay? Cosine is this side divided by this side over here, okay? So AC is equal to cosine divided by A, okay? So AC is equal to A divided by the cosine of phi. Okay, why? Because phi is over here. Cosine of phi is equal to the side, which I'm going to call A, divided by our AC. Okay, so just remember, where is A? A is over here. Okay, it is this part over here. Okay, this is A, this is A. Okay, now for the second part, for the next part, actually not the second, the next part over here. So this I'm going to call B. Okay, which is over here also. So this is B, and this will be C. And you can notice now my idea is that C plus A plus B is equal to L. Okay, let me just take this over here. So for the next beam of light, AC, CD, for CD, CD is equal to what? To B divided by what? By a cosine of an angle. What angle? Well, this is angle, which is phi also. Okay, so B divided by cosine of phi. What about the next one? Well, the next one is dB, right? So dB is actually equal to what? This C over here divided by cosine of phi. Okay, now what was the thing that we were trying to find? It was D, right? And you need, look, why is it phi? Look over here. If this is phi, if this is phi, then this is phi also, and this is also phi. Okay, and this is C over here, so this is C over here. So you will have that your hypotenuse, which is dB, let's say that cosine of phi is equal to what? To the side C divided by the hypotenuse, right? DC. So this is just what I did. Okay, so I hope there's no problem. So what is D? Remember, what is our goal? This is our goal, the time. For the time, we are just missing D, but D is equal to AC plus CD plus DB, right? AC, CD, this was point D, and DB. Okay, so what is AC? Well, this was C divided by cosine of phi plus this was B divided by cosine of phi, and this was small a divided by cosine of phi, right? Over here, cosine of phi, cosine phi, cosine phi. Okay, and this is equal to D. So now we can say that D is equal to A plus B plus C divided by cosine of phi. But what is A plus B plus C? Over here, A plus B plus C is actually L. A plus B plus C is equal to L. So we'll have that D is equal to L divided by cosine of phi. Okay, and now we can use it in our formula. So that time is equal to L divided by cosine phi multiplied by N1 divided by C. So this is our answer. Let's try to find it over here. L L multiplied by, remember it was n1, okay? This over here is n1, n1 over here, yes, n1. Okay, so L multiplied by n1 divided by c cosine of phi. So L multiplied by n1 divided by c cosine of phi, this one over here, okay? So this is the answer. So yeah, they put it a little bit of mathematics, trigonometry and triangle in this question over here. This was C, right? I think. So this is the answer.